In this video, I'm going to be talking about non-singular matrices, and presumably you've just, learned about linear independence, and you've done some of those practice problems. And now we're going to look at, rather than a set of vectors and making some sort of judgment about them, we're going to be looking at a square matrix. Okay, so this is going to be this non-singular property of a matrix. It's going to only be something we can talk about if a matrix is square, and it will have a pretty wide variety of meanings, okay? And I'll probably get into some of them at the end of this video, and some of them I will wait until later in the course to tell you about. So very much like the definition of linear independence, we'll say that a square matrix A is non-singular if the only solution to the equation AX equals 0 is where X equals 0. Okay. And something else to say about this. Something that I might want to kind of go in and talk to you about is what happens when we multiply a matrix by the 0 vector. I don't know that that's something that we've talked about in this course yet. Probably should have been when we were talking about matrix multiplication if I was thinking ahead, but maybe I wasn't. So let's say let matrix B be the one I always talk about, 1, 2, 3, 4. Okay. B times the 0 vector is going to be 1, 2, 3, 4 multiplied by 0, 0, which is going to be, 1 times 0 plus 3 times 0, and 2 times 0 plus 4 times 0. And you see the way it works is that we're always going to be multiplying against zeros, and so this will always come back 0. Okay, so I'm noticing that x equals 0 is always going to be a solution to that ax equals 0 equation. But it can be the case that there would be more solutions. And that might be hard for you to believe as well. Right now, you know about real numbers. You're real experts on real numbers. The only way you can multiply two real numbers to get 0 is by one of them being 0. But that's not the truth with matrices. There are ways that we can get, we can dot two vectors and have them come back 0 if they're orthogonal, which is, in a way, kind of related to matrix multiplication, right? We could look at it as the multiplication of a row against a column. But that's kind of a different discussion. So, and that's something that we'll get into heavily in the next unit, is like, what types of vectors, if we don't have a non-singular matrix, what types of vectors do get us back to 0? And why is that happening? That's kind of one of the concepts that we're going to explore, in the next couple of weeks. So, for example, you might say, is the matrix M non-singular? And they give you a 3 by 3 matrix. Okay, and what I'm going to do is remember that we're looking for solutions to M times X is equal to the 0 vector. Now, this is related to solving the equation AX equals B, right? Where we were solving a system of equations. So what we're going to do is we're going to augment M with the 0 vector. We're going to row reduce, and we're going to see what kind of solutions we get back. Okay. And again, much like with the determining if a set of vectors is linear independent, we're probably not going to actually augment with zeros because we know that the whole time we're just going to be lugging around a bunch of zeros and they're not going to change. But I'll let you see that on your own. So I'm going to row reduce 1, 2, -3, 2, -2, 1, 1, 1, -1, -2, augmented with a column of zeros. What I'm going to do is I'm going to actually start in on this because I've already got the matrix 1, so I don't need to copy it. So row 2 minus 2 of row 1. I have 1, -2, 1, and I'll have 0, 5, and -2 would be -3. And then I'm going to take row 3 plus 3 row 1s. So I'll have 0, -5, and plus 3 would be +1. -2 plus 3, yeah. Okay. Then I'm going to add row 2 to row 3 to kill off that -5. And 1, -3, and then we go over here, and that's -2. And hopefully you can see by this point you've row reduced enough matrices. You can see where this is headed. You can see that I'm going to divide row 3 by -2 right here. And I'm going to get a 1. And then I'm going to use that 1 to clear out the -3 and the +1. And there's not going to be any consequences over here in this column because it's all zeros. So I can say I'm going to, basically go in and erase my red annotations. And I will say, okay, next, I'm going to just say that's 1, 0, 0. Got that over to be a 1. These are all going to be zeros. And then when I add 3 back up here and subtract 1 over there, then I'll have zeros. And then I'll have a 0, 5, 0, and a 1. Okay, so then that 5, I'm going to do the same thing. I'm going to divide this row by 5, and I'll have 1. And then I'll add 2 of these up there, and it's just going to kill it off, and it's going to get me back to the identity matrix, which is, of course, saying that my x that I was looking to find is just 0, 0, 0, which is the definition of the three-dimensional 0 vector. So the only solution to mx equals 0 is x equals 0, meaning m is, in fact, non-singular. Now, I've got a couple of things to say about this. I guess I'm going to zoom out so I can write them in. Okay, first is that what you're going to be doing is you're just going to be row reducing the matrix to see if it's row equivalent to the identity. Okay, I feel like I have provided you enough reason to believe the fact if a matrix A is non-singular, a little more room, and n by n, then A is row equivalent to the n by n identity matrix. It can be reduced to the identity. Okay, there's a bunch of other facts that are relevant as well. A non-singular matrix will have a well-defined inverse. It'll have a non-zero determinant. It'll correspond to, when we're solving a system of linear equations, a unique solution. There's a lot of things going on here that you could, I think all of those that I mentioned, that you could see why that's true, just in terms of what you know so far in the course. But the other thing I want to point out, just to play this off of the previous video, is that if A is non-singular, this is very similar to looking at, if instead of starting with M equals a matrix, if I had started off with a set of vectors that were the columns of N, then I would have just shown that the column, that set of vectors was linear independent. So what I'm going to say is the columns of a non-singular matrix they're linearly independent. In the event that we found a singular matrix, what you would find is that it was not able to be reduced to the identity matrix. Okay? That there was going to be some other non-trivial solution to AX equals 0. But I think that I'm going to just stop right there and just, the definition, one where it row reduced down and came back well. I don't know, maybe I'll go back and I'll give you one where it's clearly going to be a singular matrix. And I'm going to use those linear dependent vectors that I used in the previous video. So I believe that was 16, 4, and 8, 2. So what I'll do is I'll say B equals 16, 4, 8, 2. Okay, B is going to row reduce to, we already did this the once, so it's going to be 1, 0.5, 0, 0. Okay, row reduces to that. That's not the identity. So you could just, if you were just asked if it was singular or non-singular, you could throw up your hands and say, okay, there's going to be a non-trivial solution to Bx equals 0. It's going to be singular. Okay, but what else? I had something else to say about this. oh, so it's any sort of situation where x1 plus half of x2 is equal to 0. Okay, so let's just say, for instance, x2 equals negative 2x1 was pretty much how I'd written it in the other context. And so I'm just going to choose x1 equals, I'll choose some other number. Like, how about I choose x1 equals 10? That might have been a mistake, but I'm going to go with it. 10 and negative 20. I think this is going to be all right. Because 16 times 10 is 160, and 8 times negative 20 is negative 160. That's 0. Then I go over here, and I get 40 minus 40 is also 0. So there is a non-trivial vector that, when I multiplied it by this singular matrix, got me back to the 0 vector. And eventually we'll go to say that 10 and negative 20 is in the null space of B, but you don't really know about that yet. So I think that's just a situation where, okay, my conclusion is B is singular. And I'm going to stop there. And that's going to be all for this video.